Hello, my name is Catherine Good. I am a PhD candidate in statistics at Iowa State University, and I am also a research and development intern with the Department of Statistical Sciences at Sandia National Labs. In this presentation, I will be discussing my research with Sandia that I am working on with Daniel Rees and Joshua Zalwig. Our research focuses on providing explanations for predictions made by a neural network trained using functional data. The approach we take is generalizable to any machine learning model, but in this talk I will focus on an application in national security where a neural network is used as the predictive model. I'll start by introducing the motivating application from national security and briefly discuss explainability in a general context and in the case of functional data. Then I will introduce our approach for explaining predictions from machine learning models in applications with functional data. Next, I'll present the application of our method to the national security example. And finally, I'll discuss some concluding thoughts about the strengths and weaknesses of the approach and future research directions. The application that motivated the work in this presentation has an objective of identifying characteristics of explosive devices using what are referred to as optical spectral-temporal signatures. The figure on this slide shows examples of such signatures that were simulated. The idea is that each function in the figure corresponds to an explosive device. When the explosive device goes off, a video of the explosion can be taken, and then a value, which is referred to as intensity here, can be extracted from the video over time. This creates a function such as the ones shown in the figure. Now, the shape of a function is affected by the type of explosive device used. For example, the timing of the peaks and the overall intensity are known to be affected by the type of device. Thus, the shape of the function provides information about the characteristics of the explosive device, and it is of interest for national security regions to be able to use these types of spectral temporal signatures to identify explosive devices in practice based on videos of explosions. The current practice to achieve this objective is to use heuristic algorithms and subject matter experts to try to determine the explosive device characteristics given a spectral temporal signature from an explosion. However, there is a belief that predictive performance can be improved or enhanced by using machine learning algorithms. There are various qualities that will be desirable of a machine learning model used for this application. It will be important that the model returns accurate predictions, as is typically the objective with machine learning models. Additionally, since this application is a matter of national security, it is just as important to have a model that returns uncertainty with the predictions and to also be able to provide an explanation for the predictions made by the model to assess and motivate the model. This last quality of being able to understand the predictive process is the focus of my research and is what I will discuss in this talk. In case you are not familiar with explainability, I'll provide a brief overview. The ability to interpret a model provides numerous advantages, such as being able to understand how the predictions made by a model relate to input features and being able to assess the trustworthiness of a model. Linear regression models are examples of models that have inherent interpretability since we are able to use the coefficients to relate the features to the response variable. On the other hand, many machine learning models, such as neural networks, lack direct interpretability due to the nature of their complicated predictive algorithms. However, just as in the national security example I have discussed, there's often a desire to be able to provide an explanation for how the model produces its prediction. This has led to an explosion of research by individuals working to provide ways to indirectly understand how predictions are made by these uninterpretable black box models. I should note that I usually make a distinction between interpretability, which describes models with direct interpretations, and explainability, which describes indirect ways of understanding how a model makes predictions. However, not everyone makes this distinction. In the application we are working with, we have functional data. That is, each observation in the dataset can be thought of as a function. In our case, they are functions over time, which is common with functional data, but the functions may also be functions over space or other dimensions. This ability to collect functional data has become much easier with modern technology. For example, wearable devices such as glucose monitors and activity trackers are providing loads of functional data. It is possible to aggregate the data and perform more traditional statistical analyses, but this has the disadvantage of losing some of the information gained by collecting functional data. In our example, we would like to maintain the functional form of the data and perform an analysis that includes information provided by the natural functional structure of the data. While I mentioned that there has been a lot of research done in the area of explainable machine learning, there is not really any literature focused on explaining machine learning models with inputs that are of the form of functional data, and that accounts for the functional structure of the data. This has led us to develop our approach that is able to do just that. Before I discuss our approach, let us consider a naive approach to explainability with functional data. While the figure I showed earlier depicted smooth curves over time, the data actually contains discrete time values, as is the case with functional data in practice. It would be possible to use each time point as a feature in a machine learning model. Then other common explainability methods could be used. For example, feature importance could be used to identify important time points. However, this does not provide the model with the knowledge that there is actually a natural ordering of the values associated with an explosion. Additionally, as would be expected with functional data, the vectors of times are highly correlated in our application. The figure on this slide shows the correlation between every 25th time point in our data. As you can see, up until the last few times when all of the functions are going to 0, the correlation is very close to 1. Many of the explainability methods have been shown to be affected and possibly biased by correlation between variables. And in fact, there is research being done to fully understand how and why correlation in variables affects explainability methods. As a result, this approach to training a machine learning model with functional data and not accounting for the functional nature of the data could lead to biased or non-meaningful explanations. Now, let me describe our approach to alleviate these issues. Our approach combines the techniques of functional principal component analysis, or fPCA, and permutation feature importance, or PFI, along with visualizations of the functional principal components, or fPCs, to train and explain the model in a way that accounts for the functional nature of the data. As I mentioned earlier, this approach could work with any machine learning model, but we have only focused on neural networks for the time being. Before I get into the procedure of our approach, let me provide some background on fPCA and PFI for those of you who are not familiar with these techniques. fPCA can essentially be thought of as PCA with functional data. It possesses the same features as regular PCA in the sense that the principal components will be independent, and the first few principal components will explain the majority of the variation in the data. However, the eigenvectors are referred to as eigenfunctions, because now that there is a natural ordering to the variables from the functions, the principal component loadings have an ordering and can be thought of as a function with the same domain as the observed data functions. PFI is a feature importance technique that was originally developed for random forests, but was generalized to all models recently. The concept of PFI is that a feature is randomly permuted, and then the model is used to make predictions on the dataset with the permuted feature replacing the observed feature. Then the predictions from the model, when the feature is permuted and non-permuted, are compared. This procedure is done for all features and may be repeated multiple times to account for the random variation of the permutations. A feature is considered important if the predictions are affected greatly when the feature is permuted. It is important to note that PFI has been shown to be biased when the features are correlated. As I discussed previously, this would lead to an issue with trusting the feature importance values if the naive approach to machine learning with functional data was used. As a result, we approach the machine learning training and explanation process using the following procedure. First, transform the signatures using fPCA to remove correlation between the features and capture the functional aspect of the data. Then train a machine learning model using the functional principal components. After the model is trained, PFI can be applied to identify the important functional principal components with no concern of bias in the importance values caused by correlation. However, just knowing which fPCs are important is not enough to understand the model prediction process. Thus, we use several visualizations for interpreting the functional variability explained by the important fPCs to identify the aspects of the functions that are important for prediction. While our approach makes use of various previously developed techniques, The aspect that is novel about our research is the combination of the methods into a procedure that provides a framework for machine learning when using functional data that accounts for the functional property of the data and provides a means to interpret the functions. To better understand the procedure, I will now walk through the application of each step with the national security example previously described. I have already shown you an example of some of the simulated signatures in the dataset, but let me provide you with some additional details. The simulated dataset was generated by subject matter experts based on their knowledge of the relationship between the shape of optical spectral-temporal signatures and 3 characteristics of explosive devices. A total of 10,000 signatures were generated with 1,000 time points per signature. For modeling purposes, the signatures were divided into training, testing, and validation sets. Visually, the signatures are plotted on the log scale to better see the shapes at earlier times. I will refer to the 3 explosive device characteristics as Y1, Y2, and Y3. Y1 and Y2 are binary variables, and Y3 is a continuous variable. The solid lines in the figures included on this slide are the point-wise functional means for the levels within the 3 characteristic variables, and the bands around the lines represent plus and minus 1 point-wise standard deviation. These figures depict how the characteristics affect the shape of the signatures. The figure corresponding to Y1 is on the left, and it shows that Y1 affects the shape of the function early in time. In particular, when Y1 is true, the intensity of the function is lower than when Y1 is false. And the first peak occurs earlier when Y1 is false, which leads to 4 total peaks in the function when Y1 is false, but only 3 peaks when Y1 is true. The last 2 peaks are similar for both categories. The middle figure corresponds to Y2. It shows that Y2 affects the intensity of the signature over the entire time period. In particular, when Y2 is true, the intensity is higher than when Y2 is false. The figure on the right corresponds to Y3. The plot here shows the point-wise functional means for the 4 quartile bins of Y3. This plot shows that Y3 affects both the intensity of the signatures over the entire time period and the timing of the peaks. The larger Y3 is, the higher the intensity of the signature and the later the 4 peaks occur. The first step in the application of our approach is to transform the signatures using fPCA. This is done to convert the 1,000 features of times to 1,000 fPCs. The figure here shows the percent of variability explained by the first 10 fPCs. It is clear that the first fPC explains the majority of the variation. The next few explain small portions of the variability, and the remaining fPCs, including those not included in this figure, explain practically none of the variation. It is important to keep in mind that while the majority of the variation in the data is explained by the first few functional principal components, this does not guarantee that the first few functional principal components are the best features for discriminating between explosive device characteristics. This is where PFI will be used to identify the functional principal components that are good discriminating features. A neural network is trained for each of the 3 explosive device characteristics using all 1,000 functional principal components. All 1,000 fPCs were chosen to be included based on the point I just mentioned that the discriminating fPCs may not be the same as those that explain the majority of the variation. However, it would be possible to retrain a model with a reduced number of principal components after applying PFI using the knowledge of the fPCs that explain the most variability in the data and those that are important for discrimination. The neural networks we trained contained 3 layers with 50, 40, and 30 nodes in the layers respectively. The figure on this slide shows performance metrics from the 3 models. We considered accuracy and F1 values for assessing the models for predicting the binary variables of Y1 and Y2, and we used MSE and R² for assessing the model for predicting the continuous variable of Y3. All models performed very well on the training, testing, and validation datasets. This is to be expected considering that the data is simulated and doesn't have a lot of variability. However, additional model tuning would probably be required when working with real data from this application that would have a lot more variability. Once the models were trained, PFI was applied to identify the important fPCs. 10 replications were used for each feature within a model. There was negligible variability between replications, so the average PFI is reported here. The figure shows the results from PFI for the 3 characteristics and the first 10 fPCs. The remaining fPCs were excluded because the average PFI values were all approximately 0. Note that the important fPCs vary by characteristic. In particular, fPCs 1 and 2 are important for Y1, fPCs 1 and 3 are important for Y2, and fPCs 1 through 4 show importance for Y3, with fPC 2 being the most important. This example shows how the fPC that explains the largest amount of variability will not necessarily be the best discriminating variable. However, based on the knowledge gained from applying PFI alone, it is still not possible to identify the aspects of the functions that are important for model prediction. To do this, we can use visualizations of the fPCs that are identified as important to interpret them. Here, I consider visualizations for fPCs 1 through 4. There are 3 visualizations that we recommend that provide different perspectives for interpreting fPCs. The visualizations in the top 2 rows have been used previously for interpreting fPCs, but I have not seen the visualizations in the bottom row previously used. They are visualizations I created which I find are a nice supplement to the visualizations in the top 2 rows. The visualizations in the top row depict the eigenfunctions. The curves represent the loadings or weights from the eigenfunctions versus log time. These visualizations identify the regions where the fPCs explain a contrast and variability based on where the eigenfunction weights are positive or negative. For example, fPC2 has negative values at early times and positive values at middle and later times. Thus, fPC2 explains a contrast and functional variability between earlier times and middle and later times. fPC1 has all positive weights, which indicates that it explains a weighted average of all the times with more weight assigned to earlier times. The second row of plots depict the point-wise functional mean, represented by the black lines. The colored lines represent the functional means plus and minus the eigenfunction weights times different standard deviations. These colored curves help to understand the type of functional variability explained by the fPCs in the regions identified by the top row of visualizations. For example, the plot for fPC1 identifies that fPC1 captures the variability in different intensity levels with a focus on earlier times. On the other hand, fPC2 captures the variability between observations with 3 versus 4 peaks and different timings of the peaks. The third row of visualizations include the observations in the data associated with the 50 highest and 50 lowest fPC values. These provide examples of observations that are at the extremes of the functional variability captured by the fPC. For fPCs 1 and 2, these figures help to solidify the understanding of the interpretations of the second row of plots that I just discussed. Again, the plot for fPC1 shows that it captures the variability between observations with different intensity levels, especially at earlier times. That is, the blue observations have high intensities at earlier times, and the yellow observations have low intensity at earlier times. For fPC2, we see that the contrast is not so much in the variability between intensities, but the shape of the functions. The blue observations only have 3 peaks that all occur after the mean function, and the yellow observations have 4 peaks that all occur before the mean function. To reiterate, fPC2 captures a contrast between observations with 3 peaks that occur after the mean and observations with 4 peaks that occur before the mean. The third and fourth fPCs can also be interpreted in the same way, but it becomes more nuanced and difficult to interpret fPCs as the percent of variability explained decreases. So now let us connect the feature importance with the interpretation of the fPCs to gain insight into how a neural network is making predictions. For the sake of time, I will only consider the neural network for predicting Y1, but the same can be done for the other 2 response variables. Let us review some information from earlier slides. First of all, let us return to the visualization of the point-wise functional means for the categories of Y1. Recall that we discussed that Y1 affects intensities of observations at earlier time points and the total number of peaks, either 3 or 4. Now let us return to the slides with the results from PFI. Recall that PFI identified fPC1 as the most important variable and fPC2 as the second most important variable for predicting Y1. If we return to the visualizations of the fPCs, we just discussed how fPC1 captures a variability in intensity early on. And that makes a lot of sense that fPC1 would be important for predicting Y1, since Y1 affects the intensity of signatures during those earlier times. Additionally, fPC2 captures the variability between functions with 3 and 4 peaks, which is also a functional component affected by Y1. Hence, we are able to confirm that the neural network is using features that make sense from a scientific standpoint and based on the way that the signatures were generated. We showed these results to a subject matter expert who was able to understand the results and confirm their meaningfulness. This insight allows us to have trust in predictions made by the neural network model. Let me provide some concluding thoughts. First of all, we are able to use our approach to provide insight into predictions made by a neural network model using functional data that accounted for the functional nature of the data. We were able to have our results understood and validated by an SME to have scientific meaningfulness. Additionally, in practice, it would be possible to distill the results down to the aspects of the signatures that are important to the model for prediction, which could be provided to decision makers. Those individuals are likely to have little understanding of machine learning models, but the insight gained could be described to them to motivate and explain the use of a complex neural network model in the context of the data. An obvious limitation to this approach is that if a higher numbered fPC is identified as important to the model, it may be difficult to interpret the fPC. In turn, this would make it difficult to gain insight into the model. Going forward, we have various routes that we would like to explore and use to improve the approach. First of all, we have been using a basic implementation of fPCA that only accounts for the variability in the horizontal direction of the functions. The more sophisticated method known as joint fPCA accounts for both the variability in the horizontal and vertical directions of functions. This is important with noisier data, as would most likely be seen with a real dataset in our application. The top figure on this slide shows examples of simulated signatures with noise added, and you can see how there is both variability in the intensity of the functions, which is the vertical direction, and also in the timing of the peaks, which is the horizontal direction. Joint fPCA aligns the functions prior to applying an implementation of fPCA to account for the horizontal variability. The bottom figure shows the noisy signatures after smoothing and alignment has been applied. We are also in the process of applying our approach to a real dataset to determine if it will produce meaningful results, as it did with this example. Lastly, as I mentioned earlier, an additional goal of the project is to train models that return uncertainty with the predictions. For example, the use of Bayesian neural networks is being explored, which would return not only a prediction, but also a posterior distribution for that prediction. We are interested in working to understand how the uncertainty returned with a prediction could be accounted for when computing feature importance. I have included my references for this talk on the next few slides. Overall, we were really excited about the insight into the neural networks we were able to gain from this approach, and are hoping that this will be a useful method going forward. And I thank you for your attention.